Hello again, this is Math 2231 remote delivery for April 21, 2020, use substitution part 4. I encourage you to use these kind of tools to perfect your understanding and to make notes and think through the slides. And the reason I suggest that is because magic takes practice. This is the Harry Potter Hogwarts logo. And just like Harry Potter and all those fictional characters, you will learn from your mistakes and you too will make good magic. Okay, so here are 5 examples. I encourage you to pause the video, try all 5 of these. If you make mistakes, you will learn from the mistakes, and then we'll come back and see how you did. So everybody please pause and give it a go. Let's see how you did. Alright, on this one, the key to integrating the tangent of x is to realize that the tangent is the sine of x over the cosine of x dx. And if we let u be the cosine of x, then du is, the derivative of the cosine is negative sine of x dx. If I solve for dx, I will get du over minus sine of x. So you see, when I do the substitution into this integral right here, this sign in the denominator will cancel with that sign in the numerator. And so, and then this is what I call u. So what we will get is, and then we also have a minus. So this is minus 1 over u du. And that's going to be minus, that's the natural logarithm of the absolute value of the cosine of x. I skipped the step writing the u's here, plus c. Now that could also be written using properties of logarithms. You can put the minus 1 up here, and so this would be the same thing as 1 over the cosine, the absolute value of the cosine of x, which is known as the secant of x. So any of those would be useful formulas. Students should note that the same technique, and they probably should try this, is you should be able to find that the integral, indefinite integral of the cotangent of x is going to be the logarithm of the absolute value of sine of x plus c. Many times in this class I've told you that there are 3 great techniques in mathematics, and one of them is multiplying top and bottom by a common factor, multiplying top and bottom by something that really is 1 in a clever way. This is an example of this. So to integrate the secant of y, I realize that this is the secant of y over 1, and I multiply top and bottom by the secant of y plus tangent of y divided by the secant of y plus tangent of y. We're multiplying by 1. Now when I distribute here, I get secant times secant is secant squared y plus, and then when I multiply by this one, it is going to be the tangent of y times the secant of y, and this is my denominator when I multiply across. Now, if I let u be the denominator, then I can take the derivative. So du then is going to be the derivative of the secant of y, which is the secant of y times the tangent of y. And the derivative of the tangent of y is the secant squared of y. So that means if I solve for dy, I have that this is equal to du over secant of y times tangent of y plus secant squared of y. Now when I do the substitution then into this equation, what will happen is this secant y tangent y plus secant squared of y in the denominator will cancel with this one in the numerator, and this is what I'm calling u. So you see, magic does happen. This ends up being the integral of 1 over u. And this is the natural logarithm of the absolute value of u plus c. And this is the natural logarithm of the absolute value of secant y plus tangent y plus c. So, before we go on, it's worth noting, and students might want to try this on their own, that in a similar fashion, the integral of the cosecant of x dx is equal to minus the natural logarithm of the cosecant of x plus the cotangent of x plus c. The next problem that we had was trying to integrate this problem. Now, if we let x equal the square root of x, and that's x to the 1/2, then du is, I take the derivative of x to the 1/2, it is 1/2 x to the minus 1/2 dx. And you see this 2 is in the denominator, and this square root of x is in the denominator. So if I solve for dx, I get 2 square root of x times du. So I start doing substitution, and you see this square root of x in the denominator will cancel with this square root of x in the numerator, and I will pull this constant of 2 through the integral, and then I will have 2 integral of cosine of u du. This is going to be 2 sine of u plus c, and then I have to back substitute to my original native variables, and so I will replace this with the square root of x, and I have solved the problem. You might be tempted on this problem to let u be this, but then du is this, but if you try that, magic won't happen, and you'll learn from the experience that magic won't happen. The correct approach on this problem is to realize that e to the a number plus another number is the same thing as, these are properties of exponents, e to the t times e and e to the t. See, because I would just be adding those two, and the base would still be e dt. So you see, if I let u be e to the t, then du is going to be e to the t dt, and if I solve that for dt, I will have du over e to the t. Now you see, if I put this in for dt, this e to the t in the denominator will cancel with this e to the t in the numerator, and I am calling e to the t u. So you see, this expression becomes the integral, the indefinite integral of e to the u du, and we know what that is, and then we do a back substitution to the native variable, and so the answer is e raised to the e to the t plus c. Here's the problem that we were confronted with at the beginning, and this time there's actually what I would call almost a double substitution. When someone comes in to ask me a question about this in the Learning Commons, I invariably will tell them that I will ask them, what class are you in? Because if they're in Calc 1, I will talk about doing this one way. This also could be done by integration by parts, but that's a Calc 2 topic at the College of DuPage. But we're doing it using Calc 1 technology. So if we let u to equal the square equal x squared plus 1, then du is equal to 2x dx, and that means that dx is equal to du over 2x. Now when we substitute that in, trying to make magic happen, we will get u to the 1/2 here, but what will happen is this x will not totally get rid of this, and so you say, oh, magic didn't happen yet. But if we know that u is equal to x squared plus 1, that also means that x squared is equal to u minus 1. That's why I'm calling this a double substitution. So you see, I can go from this one, and I can replace the x squared with u minus 1, and that's u to the 1/2 du. I can distribute this. This gives me u to the 3/2 when I multiply minus u to the 1/2, that is du. And then I go through and I integrate this term by term. This is add 1 to the exponent, divide by the new exponent, and this is minus, add 1 to the exponent, divide by the new exponent, plus c. And then I must substitute back into my native variable, so everywhere I have u, I'm going to write x squared plus 1. This is the answer to the problem. Okay, we come to this set of examples. There are 4 more. Again, you should pause and we'll talk through these. So this was the problem that we were confronted with, and if we let u equal the natural logarithm of x, then du is going to be 1 over x dx, and that means if I solve for dx, that is going to be x times du. Now you see, this x in the numerator will cancel with that x in the denominator. Magic will happen. This is going to be 1 over u du. It's going to be the natural logarithm of the absolute value of u plus c, and so that's the ln of the absolute value of the ln of x plus c. Here's the problem that we were confronted with, and the solution, something that will work this time, is to try u is equal to 1 plus e to the 2t. Now that means that du is equal to 2e to the 2t dt, and if I solve for dt, this is going to be in the denominator, so dt is equal to du over 2e to the 2t. So when I make that substitution, this e to the 2t in the denominator will cancel with this e to the 2t in the numerator. Magic will happen, and I will pull the 1/2 through the integral. I'll have 1 over 2. This is the integral of 1 over u du, and that's going to be the ln, the absolute value of u, and then I will replace u with what it was in my native variable, and so this is the answer to that problem. This problem you may have had some experience crashing and burning on, but a key to this problem is realizing that e to the 4t is the same thing as e to the 2t whole squared. So that means that the integral that we started out with can be looked at as being e to the 2t over 1 plus, this is e to the 2t whole squared dt. So if I let u equal e to the 2t, then du is equal to 2e to the 2t dt. That means that dt is equal to du over 2e to the 2t. So when I make that substitution, this e to the 2t in the denominator will cancel with this e to the 2t numerator. And I will pull this 2 through the integral, and I'll have 1 over 1 plus u squared du. And I recognize that this is the integral of the inverse tangent of u, and then I back substitute with what I let u be, and this is the answer to the problem. Here's the problem I started out with. If I let u be the arc sine of x, or the inverse sine of x, then we learned that du is equal to 1 over the square root of 1 minus x squared dx. That means that dx is equal to the square root of 1 minus x squared du. When I do the substitution then for dx, this square root of 1 minus x squared in the numerator will cancel with this square root of 1 minus x squared in the denominator. And then we were just left with the indefinite integral of u du. And we know how to do that. Add 1 to the exponent, divide by the new exponent, and then we back substitute with our original native variable to find the answer. So the answer to this is 1/2, that is the inverse sine of x whole squared plus c. Now, almost concluding thoughts. That was a lot of material, but it is important curriculum, so please engage. It might take you a while, but work through it. There are 3 more weeks until final week, counting this one. You can do this. My advice to everyone is finish strong. You can do this. Your goals need not be deferred. Next time, I'm going to be talking about 3 more topics envisioned. 2 of them are technical topics, talking about computing definite integrals using the substitution method and an application of that. And then I'm also going to talk about a topic called separable equations, because I'm supposed to cover that. I want to teach you a good course. I'm also going to invest some time next time talking about assessment considerations looking forward. I think people will be interested in that administration discussion. Note that I have pushed you hard, but I have allowed some time for a pointed review for the final. Details will be forthcoming soon, and in fact the details begin with this discussion next time. Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of